Great. Well, next up is John Bender. John was one of Jens's PhD students. Graduated, what, five years ago? Okay. And doing lots of cool and difficult stuff with proving things about concurrent compilers. Yeah. Okay. John.
Well, thank you. So first thing I'll say is if you find all of this sort of laborious and overly detailed and exhausting, take your complaints to Jens. None of this would have been possible if he hadn't been kind and invited me into his program for a PhD. Do I need to just unplug it and replug it maybe?
Yeah, that's not sure.
This is the best game possible. I'm right in the middle of my jokes. All right, success. More importantly though, when I started my PhD, I didn't even know how to do a proof. So I remember picking up I remember picking up the book, How to Prove It, literally, just to make progress here. And do you want to futz with it? Yeah. Okay. This is going to be a short song and dance. Anyway, over the course of my PhD, we went from doing analysis with regards to memory models. Let's hope it stays that way. And I think at one point I was like, hey, Jens, I'd like to do something more theoretical. My presentation is going to remain theoretical here as well. And I remember very distinctly Jens being completely open to that. Like, again, I had no background in it at all, but he was totally open to me trying. We did a lot of great work. We ended up with a very nice paper about Java's memory model of all things, which is, there's a lot of theory in that paper that's almost the entire thing. So, and a lot of nice lemmas and theorems. And I do most of my work today now in Coq. Okay, we're going to hope that works out. Okay, great. Wonderful. Okay, so anyway, all that is to say, let's talk about CompCert in the context of concurrency. My goal here is really, I'm just going to introduce the problem. This is a presentation that probably needs like a full day to honestly get through all the details. So we'll just start with the problem and see where we get. Okay, so just to start, everybody, I think people are familiar with CompCert, but in general, there's this nice paper about a tool called CSmith that found a bunch of bugs in compilers, right? Okay, so we know that bugs exist, and a nice thing to have, in certain contexts is a compiler that guarantees with some reasonable assurance, for certain properties that those things will carry down, that you won't have bugs with respect to, maybe reasoning you've done about your code. CompCert took a lot of work. Compilers, even relatively simple compilers or complex pieces of software, so much more the effort to do the proof along with that, right? So there's a big picture here. This is just sort of supposed to evince the fact that it's a complicated project. But most of the work is in the proofs. Okay, so that'll be important later. Famously, it only works for single-threaded programs. So if you have threads, sorry, you're out in the cold. And vaguely, threads and concurrency are important. I see nodding heads, so that's good news. I don't have to fight about this point. Okay, great. So let's talk a little bit about this. So I'm not the first person to attempt to address this problem. Like our group is not the first set of people to address this problem. So like, what are they doing in prior work? Okay, so Andrew Appel and his group had done some work on this. The kind of core assumption there was that in the memory model, all your programs would be well synchronized, right? So if you are familiar with program analysis or doing any kind of concurrent programming, making sure that your locks all work together well, that's quite difficult. Separately, there was this work from the folks at MPI. I'm a big MPI stan. I like Derek Dreyer's group. They do good stuff. But they attempted to kind of do this, but and I'll talk about the way the caveats for their work, but they ended up kind of having to shred large parts of the compiler for the proofs. Like the proofs weren't going to work in the context of how they designed the semantics, right? So that won't work for us. I don't want to rewrite large parts of the proofs of CompCert. At most, I want to have things that are adjacent to the existing proofs. So that kind of falls outside our sort of desiderata. Okay, so yeah, our goal is we want to take the proofs that exist in CompCert that are about single-threaded programs. We want to take that reasoning and we want to lift it up to multi-threaded programs. And I want to do that in a way where I don't shred the existing proofs, because those are exhausting and laborious to put together. And so as a consequence, we can also pull in upstream updates, right? So if people are working on CompCert, they're doing things constantly, making it more interesting, improving it. if I shred the proofs, it's going to be really painful to bring in updates from upstream. Okay, so there's software concerns, but it makes the problem, slightly more interesting. Okay, great. So let's talk about what it means for a compiler to be correct in the first place. I am not going to assume a whole lot of knowledge about this. Even people in programming languages have like a vague intuition for what this means, but we'll make it a little bit more concrete. Okay, so vaguely, the big black arrow is a compiler. We're going from C to some instruction set architecture. Okay, and vaguely the goal is all the reasoning that I did about my C program should carry forward to the output in my ISA. And reasoning could be broadly construed here. The details of which properties apply, what types of properties apply is subtle. We could talk about that offline if we want. So from invariance to safety properties to even liveness properties in certain circumstances, which you can get with the simulation in CompCert. Okay, but the basic way this works is, if you have some state in your instruction set architecture at that level, and it makes some it makes some step or does some work and produces some observation O, then supposing you have some equivalent state in C, roughly speaking, equivalent state in C, related by some simulation relation, then you have to show, the gold part is you have to show that you can take a step with the same observation, so those O's have to be identical. Keep that in mind for later. And then those final states are equivalent, right? Okay, so if you've ever encountered simulation, this is like roughly the thing you would expect. The idea here is that if we start with the assumption about the instruction set architecture step, and then we're going backwards, that's the backward simulation, which produces a subset sort of roughly of behaviors, right? So, and with that subset of behaviors, then our properties that we proved about C will carry down to the behaviors of the instruction set architecture. Okay, so this is what compiler correctness, roughly is broadly construed. Okay, so that's the background. Okay, so in CompCert in particular, they have a requirement, which is that all of the target semantics for the compiler passes have to be deterministic. And the reason they have this is because they don't do a backward simulation proof. They don't start that way. They do a forward simulation proof and then derive a backward simulation from that. And the reason that is because going forward is easier. When you do induction in the forward direction, you're doing it over just a program. Whereas if you do it in the backward direction, you're doing it over something optimized, right? So you have that extra painful step to deal with. So what they do is, and again, there's this, total aside here, this is like fun historical fact, but like a reasonable question is, well, could we do one with a backward simulation and avoid that? And the answer is surely, but this is the one we have. And up to the point that people had, CompCert existed, people wondered if a project of this complexity doing verification was possible at all. So anyway, that's an open question. Feel free to try it for yourself. Okay, so it's required to be deterministic because of the way they derive a backward simulation from the forward simulation. Okay, we can talk about, if you want to hear the details of that, I'm happy to talk about it after the presentation. But for now, just know that determinism is important. And obviously, maybe you see where this is going. Concurrency is not particularly deterministic. So, okay, so we're going to keep that kind of fact up in the top right there for reference. But okay, so let's see, what does it look like when we have a concurrent program? And why is this a problem? Okay, so again, this slide's maybe not really for you guys. This is a little bit more introductory. But anyway, if you have two writes to a particular variable and then you have a read to it, there's obviously non-determinism even in the single thread semantics on the left, right? Because there could be two values that X could evaluate to in that second statement, right? So that's no good. That's not deterministic. That fails our kind of criterion there for semantics. Okay, so this is the crux of the problem effectively with CompCert and concurrency, is that this requirement of the way the proof structure is set up is that there's determinism. Okay, great. All right, so someone out there will be thinking, but wait, in single-threaded programs, there are sources of something like non-determinism already, right? What if we're calling rand? We have some external source of non-determinism, right? Okay, great. This in principle, depending on how you define your semantics, this could evaluate to any number of states up to rand max, right? Okay, so how is this dealt with in CompCert now, even for single-threaded programs? Well, the key is to note that you can externalize the non-determinism, right? It's a system call. So as long as you kind of basically roughly quantify over all that, kind of symbolize the value, then you can get back a single step, right? So system calls are a special case. If you're familiar with, reasoning about non-determinism in programming languages, externalizing the non-determinism is like a trick you use to, work with equivalence, right? So this is an old trick. It's a good trick. And so as a consequence, it's a fairly natural trick to try and apply to this problem. Anyway, so you recover determinism in this case. Okay, so the key conceit of the paper from the MPI folks was, well, why don't we just do that trick again? What if here we just, so recall that this is non-deterministic. What if we just did the same trick here, where we said, okay, now reads and writes to memory are observable behaviors. We're going to externalize the non-determinism of what happens when I go off and look at memory, and maybe, you know, I'm fighting between two threads that could have written to the same variable. So we'll just externalize it, and then you get this back. So that's what that paper does effectively. The problem here is that I cut out the slides for describing the problem. Okay, so now I'm going to wave my hands furiously. Okay, so now it's part of the observable behaviors of the program, right? And you'll require, you'll notice it says T up in the top right, which is another mistake. Wonderful. The T there, which was the O in the original slide, has to be identical between the source and the target. Those have to be the same, and intuitively that's natural, right? When I compile a program, if it has some observable behavior to the outside world, it would be very bad if I was changing that, right? That's like the key way in which CompCert preserves correctness for programs. Whatever the world would observe of the program is preserved as the compiler does its operations. Okay, so that's the T, you know, previously the O being the same thing there. Okay. Here, what I've said is all my memory operations are suddenly observable behaviors, which means that in the C program, any memory operation now has to appear as an observable behavior in my target program for the ISA, right? Well, that's a comically bad idea for, you know, a compiler, right? Because one of the things that compilers do quite a lot is move around memory operations, remove them depending on the context, right? So suddenly you're left in, you know, with lots of compiler passes which just don't fit into the general architecture of the proofs, right? Okay, so this clever trick doesn't work in this case. All right, so let's see what we did, because, you know, key insights, whatever. Okay, so the first thing we realized is, well, you can't externalize it according to the steps in the semantics with this like notion of observable behavior, but you can advantageously guess a lot of non-determinism and then just stuff it into the single thread. And then if you make all the, basically, if all the non-deterministic choices the thread would have made about reads and writes and these pairings, or, you know, interleaving, is part of a guess, you can give that to a thread, and then it doesn't need to make any non-deterministic choices, right? It suddenly has all the non-determinism, and everything after that is deterministic, right? So first thing we're going to do is we're going to create a prophecy of all the non-deterministic choices. Okay, so that's the first thing here. So what does that look like? Okay, so how am I doing on time also? All right, I might even be able to get through part of how we solve this problem. This is incredible. All right, so a standard concurrency semantics looks something like this. And Jens at this point will be very happy to see that the validity predicate that you would expect from a memory model is like left off to, you know, as an exercise for the reader after my PhD. So okay, so you have a list of threads, you have some memory representation, and then at the top here, you're going to have the thread is going to do some operation. It's going to tell you, okay, I did a read, and I'm pairing with this write on the other thread, or, you know, I got the value 2 as opposed to the value 3 or value 1. And then you're going to have the memory model say, yeah, that event is acceptable, right? That's an okay pair, you know, it's an okay pairing of a read and a write. That fits within the constraints of our axioms for the memory model. And then that allowed you to take a step in the concurrent semantics. Okay, but the key problem here is, again, non-determinism, right? So the thread is doing some non-deterministic behavior. So anyway, what we're doing is we're just, this took a while to figure out, but is really kind of like trivially simple in retrospect. What we're doing here is we're just inverting the relationship. We're going to do the guessing outside the thread. Okay, and this has lots of subtle implications later that we won't even get to, but we're just not letting the thread do the guessing. We're going to do the guessing at the concurrent level and tell the thread what it's allowed to do. Okay, and the good part about that is that now the thread gets to be deterministic, right? And so the key thing to remember is that CompCert is all its semantics are single-threaded, and now its determinism is, you know, recovered effectively. So we get to hopefully keep those proofs with a minor modification, which is this parameter of the memory state that it needs to do its operations. Okay, great. These are the rest of the key insights. The one we'll get here is the second one, I think, and then the third, fourth, and fifth we probably won't get to. Okay, anyway, I think I put this list here because there's a lot of stuff you have to wade through after you make this kind of like first insight, right? It's like one kind of cascading minor issue after another you have to kind of sort of solve all the way out to the end, which we effectively have done. I'm happy to talk about later offline if y'all want. Okay, so let's talk about this. So what we've said here is that we're going to come up with, we're going to guess some memory, right, at the multi-threaded level. But what we're really saying is also we're going to have like some memory state we're going to pair with the program. And there's going to be some quantifier here, you know, roughly that says something like, if the target has some memory at which it's able to do a step, then the source, there exists some memory and some related memory at the source that allows it to also take a step. So the key thing is we've introduced this existential up here, which that would constitute a large modification to the existing proofs, right? Again, that's our goal here, is to do as little surgery there as possible. So that's bad. Okay, old trick, we scolemize. We just basically, we ask the people who are doing the pass to give us on the side a definition of how we should be mapping memory back. So suppose you made a pass and it was reordering writes and reads. Now your memory mapping going backwards has to basically reverse that process. Okay. But keep in mind, it's got to be a general thing. So we're going to run into that here as a problem. So, okay. So the rest of this is, how am I doing? I think I'm doing okay. How much time do I have?
You've got 5 more minutes if you want 5 minutes. 5 more minutes of talking and 5 minutes of questions.
Okay, so that depends on how confident I am in answering questions. All right, let's see. I'm totally confident in answering questions. I'll just ramble here for a few more minutes and then we'll stop and that'll be how it goes. Okay, so we have some other properties here. So the first thing is that, okay, so now we have this mapping. We've solved this sort of existential problem with another old trick, which is to scolemize. But this, at the end, when we do this final proof, where we lift the single-threaded proof of the compiler into a backward simulation for multiple threads, this is going to be effectively the composition of many passes, and thus like many mappings, right, that we've scolemed, these scolem functions. So we're not going to know anything about f. Or I mean, even if we could know something about f, we could inspect it, I suppose, but then it's going to be very complicated and annoying. So what we want to do is come up with some general principles about this mapping that will allow us to do the lifting proof in a sort of straightforward way. And then as long as all the mappings adhere to these principles, those compose in a nice way along with the mappings themselves, then we can get the proof at the end. So the kind of core one of these is like a notion of monotonicity, which is that if you're doing a mapping between a target and a source to kind of generate the memory it needs to take a step, you don't want to do weird things effectively, right? You don't want to cut off behaviors. You don't want to foreclose. You don't want to end up with less information effectively for the step in the program to happen. So that's like the core conceit here. And then this is like, this along with the definitions for the prophecy is what allows us to basically get the proof to go through. And then there are some implications about this later where I'm completely leaving out what the preorder is here. So that defining the preorder actually turns out to be maybe the hardest part of this whole problem. So that's like the next thing. Do we want to like suffer through this? Good question. I feel like everyone out there is falling asleep maybe. Okay, so anyway, let me just say this about the preorder very quickly. You can look at the bottom of the slide. A very natural thing to do would just to order memories by extension, right? So bigger memories, you're farther along in the program. Okay, that has a very natural counterexample if you reorder stuff within your memory, right? If your optimization is doing the reordering, if you apply the mapping to unreorder it, it's impossible to find an extension. So these kind of like a sort of naive approach won't work in this case. So anyway, we have to go on to address this. We do this through predicating the preorder, and then we have to come up with a theorem about the composition of these monotonicity predicates and things. Okay, cool. Fairness, all right, this matters. So the details of this I do not have time to get into, but fairness and safety are very important in the proof of the compiler as it exists now. So you have to derive some notion of safety for a single thread from multi-threaded safety to get this to go. This turns out to be thorny and subtle, but interesting also at the same time. And then, so the main thing is what we have left. We need to, we want to alter some of the way the preorder is set up for cleanliness, this safety issue that I was talking about. And then, we want to move on to actually implementing in CompCert. So we've done this with like a toy language with the actual structure of the proof from CompCert, but you can instantiate that with any language you want. So we've done that. And that's it. So this is a thank you for you all, but it's especially a thank you to you, Jens. I really appreciate this. I love my job. I love working on these things. And I simply wouldn't have the opportunity to do this if it weren't for Jens taking a chance on me getting a PhD. So I really appreciate it. Thank you all for listening.
So this is super cool. So you did this for sequential consistency concurrency, I suppose. So
the cool, so at first I was like, let's do x86, and then I got bogged down, and it just turns out that the whole thing is parameterized by the validity predicate. So we just abstract out and say like, please don't. Like that's like another paper you can go read, and there'll be one. In practice, what'll end up happening for the actual compiler is we'll choose probably a release acquire fragment of C++, because then you avoid the thin-air read problem, because then you have no reasoning principles at all. So yeah, that'll be the basic one.
That's very nice.
Yeah.
Okay.
So we have a story for that at least.
Super cool. Can I ask how big is your group working on?
It's me, and I have had 2 interns.
Okay.
It's basically me. Yeah, no. That's not true. That's not true. That's not true at all, actually. The 2 interns I've had, Eleanor Tang is at CMU now. She's super excellent, really excellent. And then Anjali Paul is at UW, and she's working with me year-round now. So these people were excellent. To even characterize it as me doing it on myself is silly, honestly.
More progress is going to happen. This is cool.
Let's hope so, yeah.
Yeah, cool work. It's, I guess, very similar to Jens's question. So you said it's parametric on the memory model. Have you thought of how to pass the parameter, not just as an enumerated set to choose one of these from, but maybe a model in, say, herd or something?
So as a default, you would sort of assume that whatever the model is, it'll be one of the axiomatic models you would grab off the shelf. However, it's worth noting that there already exists an intermediate memory model project, I think also from like the line of people from MPI, where they did the work of saying, okay, here's the C memory model, and then they have the like outputs for all the, this sort of like the refinement outputs for all the various architectures. And I expect that we're going to need that at some point anyway, even if we just sort of fix an architecture and move on with our lives. So to your question, yes, we've thought a lot about like the ways that validity predicate will matter in the future for the project. Yeah, that's a great question.
Maybe I'll just ask one question. So one of the motivations, which makes a lot of sense, is that you want to be able to reuse much of the single-threaded reasoning. So can you give a sense of like, let's say there's a constant propagation optimization already in there.
Yep.
Like what in general does it take to then make that safe in a concurrent setting? Okay,
so one of our parts of our research proposal is that we made we hypothesized the amount of code changes required. So one thing we already identified is that you have to add this parameter to semantics everywhere. So that's one thing. Otherwise, the lemmas and everything about the mapping and stuff should exist entirely off to the side. I think there's a big open question I have right now is locality, right? So one thing is if I know the memory is going to be local, I should just be giving the mapping should just be the identity mapping, right? I don't want to deal with that. I don't want to have to do any extra proving in that case. That I have not sorted out. And that is an open question. This is like the key question right now is like, what is the actual impact on doing the compiler? In principle, we've left it almost all to the side. In practice, I still have to figure that out. This is a really great question.
Okay, let's thank John again.
Thank you all.